Thank you everyone for joining our seminar today. Today we have a very interesting guest, Dr. Eike Schneiders, who's an assistant professor at the School of Computer Science at University of Nottingham. I know Eike from my time at Aalborg University. And I know that he's done very interesting research in human-robot interaction for several years now. Today he'll be talking about entrainment in human groups and how we can use that knowledge to design human-robot collaboration. So without much further introduction, I'll give it over to Eike. Looking forward to your seminar.
Thanks. Yeah, good morning or afternoon, everyone, depending on where you are. For me, it's currently 7 a.m. As Stine said, my name is Eike Schneiders, and I want to start by extending my thanks to you, Stine, for organizing this and giving me the opportunity to present to the Southern Hemisphere for once. I'm an assistant professor from the University of Nottingham, and on behalf of my co-authors, Christopher Faree and Julie Shah from MIT, as well as Stanley Celestin and Malte Jung from Cornell University, I have the pleasure to present our recent Chi 24 paper titled Understanding Entrainment in Human Groups, Optimizing Human-Robot Collaboration from Lessons Learned During Human-Human Collaboration. And this research was a joint effort between these three universities and received funding from the UKRI Trustworthy Autonomous Systems Hub, as well as the US Office of Naval Research. So, with a paper title starting with Understanding Entrainment, it seems like an obvious first question. What is entrainment? And Renaud and Traktinsky define it as a process of reaching the same rhythm and is a required part of synchronizing with someone else. So in its essence, entrainment is a process. And the result of that process is that agents or systems move in sync. And what makes this process so interesting is that it already happens seamlessly all around us. And some examples I'm sure you're familiar with, but examples include metronomes on a freely moving platform, as illustrated here, who start off not being synchronized, but through the process of entrainment, fall into a temporal rhythm. Another example from nature are fireflies who start blinking chaotically, but over time, the longer they blink, a rhythm emerges through entrainment. And what most of you, I assume, have experienced at some point in your life is humans walking in groups where subconsciously the steps are synchronized. All of these are examples of entrainment. So let me show you some examples where humans collaborating based on this temporal synchronization, so based on the occurrence of entrainment. So the first example that I show you is going to show two Japanese men producing mochi. So as you can see in this example, the keeping of this temporal pattern that emerged, i.e. that timing, is, for one thing, it's important for efficiency, but secondly, it's of course also quite important in this particular instance for the right man's hand. The second example shows a pineapple harvest in India. And here we see a group of more than 10 people who work in perfect rhythm, completing the task of transporting and loading pineapples onto a truck in a very efficient way. And if even one person breaks this rhythm and falls out of the entrainment, falls out of the temporal synchronization, the entire collaboration is at risk of breaking down. So this leads me to the question, why should we as HCI or HRI researchers care about entrainment? What makes entrainment interesting for the context of HRI? Well, with the increasing deployment of robots, or specifically collaborative robots, in a variety of domains, we see an increase in number of tasks happen that require collaborations of different kinds, some between humans and robots, some just humans, or in all kinds of various mixed teams. And whenever collaborating, one of the prominent problems is, for instance, the free rider problem, which in its essence says that during collaboration, some collaborators deliberately contribute less than others to the collective good because they know that the result of the collaboration will still be achieved. And however, previous research has shown that moving in sync can, for instance, address this problem, amongst other problems. And it in general comes with a vast range of positive side effects going beyond the mere increase in efficiency. So a study by Roy and Edan, for instance, has shown that a pair of collaborators during a supermarket shelf-filling task felt that their collaborating partner was equally committed to the task when they performed the task in sync compared to when the task was performed out of this temporal rhythm. And another study by Hove and Risen has shown that as little movement as finger tapping, if it occurred in sync versus not in sync, increased the feeling of togetherness and likability between collaborators, both which are desirable characteristics for effective collaboration. And finally, I want to highlight a study by Wiltermuth and Heath, who has shown that walking in sync increases the willingness to collaborate and contribute to the collective good of the group. And thereby they showed that this movement in sync, as a direct result of entrainment, effectively can counter, for instance, the free rider problem. So it becomes quite apparent that, at least in human-human collaboration, moving in sync comes with a lot of positive side effects outside of the mere increase in efficiency. But how does this tendency look when we work with robots? So a small body of prior literature exists that has shown this entrainment also can happen between humans and robots in dyadic settings as well. And examples here include Lawrence et al., who have shown that simple forth and back reaching movement can lead to entrainment between one human and one robotic collaborator. And full body entrainment has been shown to occur with the social robot now specifically by Anselm et al., showcasing that even when using the entire body, this interpersonal motor synchronization, or the physical form of entrainment, can happen between humans and non-human actors. And given this potential of positive effects, or positive side effects, if you will, when moving in synchrony, we believe that informing future research and design within human-robot collaboration might benefit from a human-centered approach by investigating which factors lead to the occurrence of entrainment. So, to do exactly this, we set out to study how human dyads and triads collaborate in fast-paced, repetitive repetitive tasks, as one might find them during, for instance, industrial assembly, restaurant kitchen, or doing warehousing tasks. And as a first step, we aimed at understanding what characterizes and leads to this entrainment of human pairs and triads, given a controlled setup using a designed task. And to develop this task, we brainstormed, sketched, and piloted 8 tasks in various configurations, and inspired by various industries such as assembly or food preparation. And we prototyped all 8 tasks and variations of it using low-fidelity material. Following this, we finally decided on 2 tasks, one being an assembly-inspired, one being a pick-and-placing-inspired task. We piloted them and selected a dyadic and a triadic version of the industrial-inspired pick-and-placing task, given that we were interested in also seeing what are the differences between how dyads and triads entrain. These tasks needed to be comparable, but more on that later. And finally, we selected one scalable task to both dyads and triads that was inspired by a pick-and-placing task, but I will demonstrate that in just a little while. So, as mentioned, in this study, we took this human-centered approach towards informing the improvement of future human-robot collaboration. And we do so by investigating the characteristics of how humans synchronize, temporarily synchronize, while completing this designed, fast-paced, repetitive task inspired by industrial pick-and-placing. And we investigated this using a lab-based study with 50 participants, 10 being part of the dyads, 20 being part of the dyads, and 30 participants being part of the triads, leading to 10 dyads and 10 triads, respectively. And each trial lasted for 4 minutes, which was unbeknownst to the participants. Each collaboration had 2 roles, regardless of which condition they were in. We had the bowler, of which each dyad or triad had 1, and we called that role the bowler, given it was the person that handled the ball, and 1 to 2 cubers, which were the participants handling small 1 by 1 by 1 centimeter sized plastic cubes. And for the dyads, we only used position A and C, with the bowler sitting in position C and the cuber in position A, while triads use position B for the bowler and A and C for the two cubers. For data collection, all of this, by the way, will make much more sense in just a second when I'm showing some videos of both the dyads and triads. For data collection, we used 2 cameras for audio-video recordings, 18 cameras of the OptiTrack camera system for motion capture of participants' hands as well as key objects, as well as post-task semi-structured interviews, group-based. Yeah, but as mentioned, the best way to get an understanding of the task is through a small video clip of the dyadic collaboration and the triadic collaboration, respectively. So let's have a look. And here, for instance, notice how the cube did not hit the collection bin, and again, it missed. Just gonna restart that. So for the first 2 iterations in this video, this one and this one, the cube doesn't hit, and we get back to the significance of that. So this is the dyadic task, where the cuber picks up a cube from a bowl next to them, puts it in the bowl that the bowler manipulates, and the bowler empties it into the bin on the floor next to them. So let's have a look at the triadic task. Same thing, the bowler sits at the end. You see the 2 cubers are not really synchronized here. There's 1 cube, 2 cube, 1 cube, 2 cube. This was already much better. This seems already reasonably in sync. Very short delays still. So as you can see, it seems as if something is happening at the distance, the temporal distance between the dropping of the cubes of the 2 cubers respectively seems to become smaller. All right. So following the data collection, as you've just seen with 10 dyads and 10 triads, the first step was to investigate if we had any differences between configurations in relation to our random allocation of participants into dyads and triads. So did we have significant differences between demographic distribution or task performance? And the reason this was important was that some of the findings I'm going to present in just a while are of comparative or contrasting nature between dyads and triads. And this means we want to rule out, or at least lower the chance that the differences we see here are caused by a significant difference in participant allocation. However, no significant differences between dyads and triads were found in relation to age, gender, and handedness. And we also did not identify any significant differences in relation to performance, with the smallest p being just 0.3, which is good because this means that given that we don't have significant differences between groups, these are somewhat comparable in terms of participant allocation as well as their performance. In this table, you see that I'm listing 10 dyads and 8 triads, and this simply happened due to technical errors during the data collection. We had to exclude 2 triads from the data collection. Yeah, and the performance was measured in this case as average iterations per 10-second interval, which was inspired by Roy and Aiden's paper. So in the paper, we present 5 findings, or 5 different findings, which I will very briefly go over in this talk today. Firstly, we looked at temporal synchronization. And to do this, we used the motion tracking data of participants' hands to identify each individual task iteration. And we considered a task completed, or an iteration of each task completed, once the bowl, so once we could track that the bowl with the cubes in was tilted towards the bin, meaning once the bowl was emptied, one iteration started and the next iteration, one iteration stopped and the next iteration started. And as mentioned, just to reiterate, we were not interested in speed, we were interested in consistency. And that means that how fast they perform the iteration is not important for entrainment. It's important that the task completion time for iteration I is as close to iteration I plus 1 as possible, and so on and so on. So we want low deviations between individual iterations of the task to classify it as a temporal rhythm as a result of entrainment. And what we see here are two graphs plotting the raw data for the dyads on top and the triads in the bottom, with the average as illustrated as a red line. And we have here just under 60 iterations plotted, given that that was the lower bound, so the group with the least iterations completed around 60 iterations. And a consistent amplitude, so the amplitude above and below 0 of each individual iteration showcases the difference in time this iteration took compared to the previous one. Meaning if the iteration took half a second longer, we will see a spike going above the 0 x bar up to 0.5. And if it's faster, it goes below. And that means that the lower the fluctuations are between subsequent points on this graph along the y-axis, the less are the temporal fluctuations between subsequent iterations. And this means that temporal fluctuations, when they are lower, this is an indication of the emergence of a temporal rhythm as a result of entrainment. And as we can see for both configurations, it seems that after an initial period of high fluctuations, a norm in iteration duration emerges with reasonably low fluctuations with just 0.5 seconds, give or take, which is also what we saw in, for instance, the triadic video. And this tendency was, for some groups, actively noted. So Triad 8, for instance, stated that, I think I kind of adjusted to their speed because at first I was going too fast. So it seems as if they were making an effort, or at least they noticed that they were changing their speed in order to fall into this rhythm, fall into this consistency. Yeah. Next, we use the interview data as well as the video recording data to investigate if there were differences in how the collaboration is coordinated, or who is setting the pace, or call it who's the leader and who's the follower. And based on this analysis, we could identify two primary patterns. The first one focusing on a static leader, and the second one on an absent leader. And for the dyads, it became quite apparent that the task of cubing was perceived as being the slower task, or the bottleneck. And therefore, this was the task that was perceived as setting the pace, or leading the tasks for most. And this was, for instance, expressed by the dyad 15, in which the cuber said, I like to believe that I set the speed. I don't really recall waiting for the ball very often. And this tendency was observed for 7 out of the 10 dyads, making this the vast majority of patterns or of ways to coordinate their collaboration in terms of who's leading. And this tendency was quite different from the triads, who reported that their primary strategy was the absence of a leader. And this might simply be to the presence of multiple collaborators, meaning it is harder to select who is setting the pace. And here, for instance, T8 very explicitly simply stated, I don't think there is a leader role. And this was, similar sentiment was expressed by a large number of triads. However, interestingly enough, and this is not a pattern, but if you will, an outlier that is still interesting, we had one triad, specifically triad 1, who said that they felt that there were multiple leaders, specifically the two cubers, leading the pace and the bowler following along. So the bowler in T1 stated that I feel that I, the bowler, kind of am the follower for their collective behavior because I was trying to match the tempo, which suggests that multiple leaders is absolutely a possibility during this collaboration. So next, inspired by Roy and Edan's study, we investigated the nature of conversation between participants, or the interpersonal communication. Did the conversation or the topics of conversation change in any meaningful way between conditions? And to do so, we looked through all videos and classified each conversational topic into one of 6 emergent categories. And we did this for both the dyads as well as the triads, resulting in the here shown Pareto diagrams. And what we can see here is that there was a significant difference among the first two groups in terms of distribution of conversation. And these are specifically small talk versus general task-related conversation. And this is quite interesting, given that small talk was the only of the 6 categories that was outside of relatedness towards the task, where the other 5 were primarily related to the task at hand. And one explanation for this could be that the move from dyad to triad increases the mental workload or the cognitive workload that is necessary to complete this task efficiently when collaborating in larger groups. And this could be indicative of a higher mental workload required in larger groups. A second explanation could be the so-called many minds problem, which has been coined by Cooney et al. In 2020. And in short, it means that the dynamics of a conversation increase in complexity with larger group sizes as the stakes of disclosing personal information increase. And this personal information disclosure would here fall into the category of small talk. And given that the stakes increase, participants might be less likely to discuss anything that is not strictly related to the task at hand, with varying group size or with increasing group size. Both of these are just speculations at this point, and would need a follow-up study using, for instance, for the first one, we could, for instance, use FNIR or EGs or task load index in order to identify the demand, the cognitive demand, and see how that unfolds and compares between the 2 conditions. So next, we looked at the point of assembly. And there's, strictly speaking, no assembly, but we define the point of assembly as the point in space in which the 2 or 3 actions meet. And this is the point at which the cubes are dropped in the ball. And as exemplified in this figure, the 3 actions meet in a very consistent position, even over the course of many iterations. It's visible here. So the first frame shows iteration 24. And 60 iterations, which corresponds to roughly 2.5 minutes later, in the lower right corner, the point of assembly is nearly the same, especially along the x-axis. On the y-axis, we have a slight drift between, for instance, frame 3 and 4, but still, there's a surprisingly high consistency, given that they weren't instructed to keep it consistent at all. So they were completely free to place the ball however they felt. And through interviews, we identified 2 strategies leading to this decision of the point of assembly. The first one aimed at optimizing the collaborative performance, while the second one was aiming to ease one's own task. And while the second one aimed to ease one's own task, that does not necessarily mean that it didn't contribute to the collaborative overall performance, but just that the motivation for adjusting the point of assembly wasn't an improvement of overall performance, but an improvement of ease of our own task. An example of this first strategy is, for instance, expressed by the bowler in Triad 2, who stated that they also optimize the location of the ball, and then we can move it further away from the bin, which is their endpoint, because it on a global sense would be the best strategy considering both of the cuber's arms. And that in essence means that the bowler, who put the ball into the center of the table and then had to drop it next to them, was willing to increase their movement trajectory, or their work, if you will, in order to facilitate an easier dropping of the cubes for the 2 collaborators, or 2 cubers in this particular case. And this means that they were willing to increase the workload for them because it, on a global sense, was perceived as being an optimization of the task. Yeah, the second strategy, which emphasized a conscious choice at making the task easier for oneself, was, for instance, described by the bowler in Dyad 11. And here the bowler stated that, later I found out I'm actually the slower one. So then I just moved the ball near me so that it's easier for me to put the cubes in. And given that this is, a clear example of the bowler making the task easier for themselves. However, as I mentioned earlier, this is not necessarily in contrast to an increase in performance on the global scale or on the entire task scale. So they're not mutually exclusive necessarily. All right. Next, we use the motion tracking data in order to see if not just the point of assembly remained consistent, but also to see if the individual trajectories going from the individual endpoints towards the point of assembly change in consistency. And what we see in this figure are 10 frames, each representing 24 seconds of hand trajectories between the 3 collaborators, in this case of triad 3. And each frame illustrates roughly 10 iterations between individual endpoints and the point of assembly. And this is the XY perspective, given that we are, of course, in 3-dimensional space. We also looked at the YZ perspective, which is in the paper, but for the sake of clarity, I just included this perspective in the slide. And as visible from the first 3 frames, for instance, in the top row, so top left corner and split 1, 2, 3, all 3 collaborators have reasonably strong fluctuations in trajectory. And this is visible by inconsistency in these individual lines, each line representing 1 hand. And furthermore, given that we see 6 colors moving, not to the same extent, but still we see all 6 colors moving, this indicates that they still haven't found their rhythm in terms of which hand even to use, which we see by the fact that we see 6 lines actually moving. And this shifted over the next few frames until we, in roughly frame 7, see a very clear, which is now more than 2 minutes into the collaboration, we see a very clear tendency to follow the same trajectory, the same path for each iteration. So if you look at frame 7, especially for the orange and the purple one, the fluctuations of trajectories are quite small, which is indicated by the low spread of the lines. They're all very much on top of each other. It's slightly more so for the light blue, but it is still reasonably consistent. And this indicates that not just the position and the timing synchronize, as argued before, but also the individual trajectories leading to this collaborative effort. The last finding I briefly want to present is related to the importance of task-intrinsic multisensory feedback, and specifically the dropping from the cubes into the bowl. So when the cubers drop the cube in the bowl, as you've seen in the videos earlier, and the bowler consequently drops it from the bowl into the bin, you have a distinct click-click sound of the plastic cubes hitting the plastic of the bowl or the bin respectively. And this was not intended by us. This was a side effect we weren't aware of before running the study. But this was perceived as high-value feedback, making it easier to coordinate the collaborative effort without having to permanently rely on visual information to identify once one iteration was completed. And this was mentioned by both dyads and triads. So for instance, dyad 20 mentioned that when she, the cuber, dropped the cube into the bowl, that's when I knew it's ready to dump it into the bin, meaning the cuber relied on, the bowler, sorry, relied on the click sound of the bowler's dropping of the cube to see that this task iteration was actually completed. And in a similar fashion, this benefited the triads, where triad 5 expressed that I think whether I knew it or not, I was cueing into that sound of dum-dum, which was the sound of the cubes dropping in. And again, this was expressed by triad 1, who also stated that. But also in this case, because I personally see the dropping of a cube as a cue, an audio cue on what the rhythm is. And interestingly, as you've seen in the dyadic video, which I will show you in just a little while again after this, the cubes didn't always hit the collection bin from the bowl to the collection bin, as shown in this dyadic video earlier. And this meant that the cubes landed on the carpeted floor, resulting in a complete absence of this distinctive acoustic feedback. And this in turn could lead to confusion or distraction, as the iteration wasn't processed as completed by collaborators. And we can see this in this video. They pause and have to rely on visual inspection. Here you even see the cuber looking under the table to see what happened. Why isn't this task completed? So the absence of this distinctive acoustic signal that indicates this iteration is completed, we can move on to the next iteration, led to confusion and distraction and ultimately a breach of this temporal rhythm that we're interested in. So based on this study, we've shown several things, which in turn led to 3 recommendations for the future of designing collaborative robots and in general, human-robot collaborative processes, all in an effort to achieve actual human-robot collaboration in close proximity. Firstly, we need to move away from these hard-coded robot behavior, but instead focus on how cobots can adapt their working rhythms in order to adapt to the human collaborators in the same fashion that humans are doing this. Secondly, we argue that we should consider how we can remove the over-reliance on visual cues by introducing other modalities to the collaboration. And our study here specifically has shown the value of indicating key moments of the collaboration, i.e. the end or beginning of a specific task or a specific iteration, through a task-intrinsic acoustic feedback. And lastly, we should consider how cobots, in order to be more legible, can maintain a short-term consistency while at the same time allowing deviations to accommodate the human collaborators' behavior in the long term. And more details on everything presented here can, of course, be found in the paper. And with that, I say thank you for your time, and I'm happy to take questions.
Thank you very much, Eike. I see that Marcus has a question.
You're muted, Marcus.
Yeah, I know. Thank you, Eike. That was super interesting, and thank you, Stine, for organising. Look, that's really interesting work, Eike. Thank you very much for presenting. I'm the co-lead for human robot detection in the Australian Robotics Centre, so we're really interested in sort of topics that relate to your presentation.
Mm-hmm.
I was really curious about the modality, and I noted that when you were showing some of the example videos, especially the mochi making one, that sound played a really important role, because clearly there was a training and there was a very trained sort of performance, but there was that shouting and the sound, etc. So, you know, it's not entirely surprising that multimodality can also play a role in entrainment when people work. I'm wondering whether you had any other sort of examples of modality in your data. I guess it's quite a sensory experience. I guess the cubes weren't heavy enough to get more haptic feedback. Yeah, that's
yes. So
question.
great question. Thanks for that. Completely agree. I mean, this mochi example, I like to show that because it really shows this case that, hey, other things than visual is quite important when humans collaborate. And the 3 modalities that I would say that our participants used the most, of course, tactile, so they were feeling the cubes. As you say, the cubes weren't heavy enough for the bowler to be able to distinguish, do I hold an empty bowl or do I hold a bowl with 1 or 2 cubes in it? But the tactile was still useful for the cuber in order to pick the cubes up. They didn't have to rely on visual cues to see, do I hold exactly 1 cube? So they absolutely used that to see, okay, what am I doing here? However, given that the task was pick and placing, you could argue, well, naturally, if they have to pick something up, they will always use tactile feedback. However, it was quite important given that it freed up the visual cues and they were allowed to, or had the opportunity to look at where do they drop it instead. Other than these 2, the acoustic one was the one that, and as I also mentioned, this was quite surprising to us. The tactile and the visual we of course expected, but the acoustic one was surprising to us as it unfortunately never happened or wasn't mentioned during the pilot testing. Again, I mean, we pilot tested 2 tasks with external people, each in the dyadic and triadic configuration. So it was quite a limited scope, of course, because we don't want to keep pilot testing without collecting data. But yeah, the acoustic one was definitely a surprise, but quite an important one, I would argue, especially given that so visual cues, especially lighting signals, are already reasonably used within industrial contexts, where audio or acoustic in general is less used as far as at least from what I've seen. You can, of course, here put the limitation in place, I guess, to this study, that this was a controlled experiment in a quiet space. Lots of manufacturing sites are not as quiet. So it's very, very much a question of how do you implement this acoustic feedback without increasing the stress of the worker because they get honked at all the time, to make this happen in a meaningful way that actually contributes to the ease and brings down the mental workload of the worker, and thereby ultimately introduces benefits other than additional stress factors in an already noisy environment.
Thank you. I do have another one, but I'm also happy to wait for other people.
I think you could just take it away.
Yeah. I'm also really interested in the embodied nature of the work. So, I mean, clearly, you know, the people sitting around the table, and it's not just the moment of dropping the cube, it's actually the movement and the intention of people sort of to move towards something. From your qualitative data and your interview data, did you get any indication that people were sort of aware of where people were in the process of dropping a cube, whether they could see that people were ready or not ready? What sort of was the level of understanding of that in your experiment?
So there is definitely, and this is not just documented by us, but this is documented also in the literature. We just show it again in a triadic configuration over the usual type of investigation. This is dyads, because for various reasons it's much easier. Still complicated, but easier than group scaling. But people were aware of what their collaborators are doing. I don't have a specific quote I can pull out of my hat now and tell you here's an example of this, but people were aware, and they were consciously at times, not for all groups, consciously making an effort to adapt. Where entrainment is typically characterized by a subconscious process, which makes it so great because it happens automatically if you want it or not. We're kind of hardwired to do that. But while this happened, people were to some extent noticing that I slowed down. I think I had one quote on one of the slides where they said, I noticed I was going too fast, so I slowed down in order to accommodate and match their awareness of where their collaborators currently are within this individual iteration. And this was, again, they weren't instructed to, you have to fall into a rhythm. We just told them, drop the cubes into the bowl, then into the bin for an undisclosed number of minutes. We'll stop you at some point. And it still happened. And that's what makes entrainment so interesting, that it happens as a subconscious effect, but when asked about it, when probed about it, if you will, some participants absolutely stated that they thought about where are my collaborators in their respective iterations, in their respective tasks, and making efforts to accommodate that and to wait. And again, when I say wait here, these tasks, I mean, within this entrainment period that I highlighted on the graph, we're talking 0.5 seconds, right? So a wait is really, really short between humans. For humans to, okay, I'm gonna wait, and then 0.3 seconds later, now I waited long enough. That's a very short time. But they absolutely had some sense of where the other collaborators were in the iteration.
Thank you.
Thanks for the question.
I see that Mike has posted a question in the chat. Mike, do you wanna okay, yeah. So I'll just read your question then. So Mika says that she's curious about your data analysis methods. How did you analyze the visual and audio data, and what type of tools do you use?
All right, yeah, thank you. So the interview data was thematic analysis. We used motion tracking for the mocap, but the audio video data, which was actually quite tricky to do, it was, if you will, a visual inspection. We relied on eLearn, which is a video annotating. It's basically a program for coding video data in order to identify key moments in task iteration for all videos, where we basically started by saying, because we have these two angles, synchronizing them, putting them side by side, which allowed us to inspect the entire area of collaboration, or the entire area, yeah, where the collaboration occurred. And we simply manually went through that and encoded the data using ELAN. Yeah, very, very, very time-consuming and tedious process that I wouldn't recommend to anyone. Yeah, I hope that answers your question. Thanks.
Any other questions for Eike? I was actually wondering about the leader role and non-leader roles, and sort of how to translate that into a human-robot collaboration setting. Because, like in a triad setup, you mentioned that in most cases there weren't any leader, and then I was thinking, well, in a human-robot collaboration, maybe we'd want there to be a human leader, or should is that something like, how do we transfer that into human robot collaboration, this sort of idea of leadership?
So, and this is of course our understanding of what we mean when we say leader, and what we mean here is basically the pacemaker, if you will, right? The person setting the pace, therefore leading this particular task completion. Completely agree, it's very tricky, and I'm not sure I have a satisfying answer to how do we now make this work. It's related, of course, to who initiates a task in a human-robot collaborations context. Yeah, it's a good one. So I think which we see here in the key takeaways, one of the design recommendations is allowing the robots to adapt their behavior on runtime, if you will, in order to accommodate. And that's not directly related to who's leading, but it's related to the robot being able to change their behavior based on what the human needs or what the human does. And I know that this is, of course, to some extent a bit idealistic, because at the end of the day, we can't just slow the robot down till near standstill just because the human feels tired, because we need to meet productivity quotas and so on and so on. But I think there's some flexibility here where we can improve on how human-robot collaboration works at the moment. Yeah. I'm sorry, I don't think I have
that makes sense. Yeah, and it's definitely there's probably not a straightforward answer to that. I was just curious. Your reflections on that.
So what I can say was maybe interesting. Christopher Fury at MIT, one of the collaborators on this paper, is currently leading basically our next paper on this, where some of these considerations, especially the one about temporal and spatial adaptability of the robot, has now been implemented into a Franca Amica, so into a Panda robot. And that will hopefully be published within a year, I say. So more on that. And it shows that people absolutely are willing to work in fast-paced tasks in very close collaboration with the robots, with a high amount of trust towards the robots, because they see, after some initial skepticism, the robot moves out of the way. They do not need to take care of the robot. They do not need to care about where's the robot currently moving. They can just do their thing, and the robot does its thing in very close collaboration, working on exactly the same parts, and it just moves out of the way, even if you break your rhythm. So it's able to read your temporal pattern and spatial pattern live, learn from that, and adapt to that on the fly. So that's definitely something worth keeping an eye out for, I think. Yeah.
Great. Well, good luck on the paper.
Thanks.
Do we have any other questions for Eike?
If you should come up with questions feel free to drop me a line. My mail is right there. Feel free to read the paper if you want to hear anything else. Also offline, more than happy.
Yeah, Eike also
answer.
did a very interesting project at the University of Nottingham around cat-robot collaboration. So if that interests you, reach out to him. They actually did a collaboration with people in Brisbane. So that as part of the World Science Festival, it was exhibited at Queen Street Mall, which was great. Sort of a live stream of cats playing with robot arms, which is really cool. All right, then please join me everyone in thanking Eike for the great presentation today. Really enjoyed it. Thank you so much.
Thanks for having me.
And I'll see everyone soon, I hope. I'll just stop the recording now.